Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we'll be going over the derivative functions, higher order derivatives, and differentiability. So we'll start the lesson off about talking about derivative notations. And there are multiple ways to represent a derivative, and some of the common ways that we've seen is this way, the f prime of x. And likewise, we can say, instead of using function notation, we can say y prime. So both of these are valid. Now there are a couple other forms. I'm going to show you all of them. Another form to represent the derivative would be called Leibniz notation. I'm sorry if I butchered that name, but it is in the form of this dy over dx, and this is not a division sign. This simply means that it is the function of y getting taken the derivative of with respect to the variable x. And we can write this again using the function name, which is f, so we could say it's df over dx. And likewise, we can say that it is d over dx of f of x. Or if we're using the common variable of like y and x, we can sometimes just get away with saying d over dx, and that would mean the derivative. All these are like the same essentially. And the last few ways actually to write out a derivative notation would be to use the capital D variable, and you'll see a lot more of this notation when you get to partial derivatives in Calc 2. So you'll be writing stuff like, okay, dx of fx, meaning it's the derivative with respect to x of this function f of x. So you'll see more about when we get to like implicit differentiation of what I mean by with respect to x, because when we take the derivative of something, it's only the derivative of a specific variable. You'll see more of it, as I said, in implicit differentiation, and you'll see a lot of it in partial differentiation in Calc 2. So now let's talk about differentiability, and the concept of it is pretty simple. We'll go over right after this the cases where you can fail to be differentiable, but a function is differentiable if the derivative of that value exists, and it's differentiable on an interval if you can differentiate every value within that interval. So pretty like intuitive stuff. I mean, if the derivative exists, then it's differentiable. If it doesn't exist, then it's not differentiable, and it would be differentiable on an interval if you can differentiate the function at every number within that interval. So now let's talk about when a function can't be differentiable, and there's three main cases for this. I'm going to go draw a example of all three cases, and then we're going to talk about them. So here are the three cases, and they are known as the corner, which I will draw in a second, a discontinuity, or a vertical tangent. So the corner, if we had a function that went something like, let's say this, at this point right here, let me mark it in red, this point right here, it would not be differentiable because it goes to a corner. A discontinuity is pretty obvious, but if we had a function, let's say it ended right here, and then it made this like jump, and all of a sudden it started up again over here. So we have this like all this in between area right here, like all this area here, that's like not accounted for, and the function would not be differentiable at these values. Lastly, we have the vertical tangent, and this is if we have a function that goes like this, like an S shape, and it would have the vertical tangent right here. This is undefined, obviously, because we would have a division by zero error. We know that for a vertical line, the slope is undefined, so this right here would fail to be differentiable because of that. So lastly, we're going to talk about higher order derivatives, and I could give an example of this, but essentially it's just you following the steps to take the derivative of a function multiple times. So if we say like, oh, the second derivative of a function, this would be like notated as f2 of x. And again, this is not a power. This just indicates what order derivative we're taking. Likewise, we can say something like f this. And normally people use these dashes until we get maybe up to like 3 or 4. Then we start putting the number there, but I'm pretty sure both are like equally valid. And using the Leibniz notation that we learned, it would essentially be just dy over dx, but we would take that of a derivative itself. Like we would do the derivative twice. We would do this one and then this one, or sorry, this one first, the inner one first. We would take this one first, and then we would take the derivative again of it. So we could write this as d squared y over dx squared. This would be the notation for a second derivative in Leibniz notation. And like if we have something written as like in the form of fnx, this just means that we take the derivative n times. So nothing too difficult. You're just going to be writing this, not writing it, you're just going to be continuing the process as many times as it tells you. So yeah, thanks for tuning into this quick little lesson. In the next lesson, we'll be going over the ways to find derivatives of certain functions. So this was just kind of an introduction to the derivative function itself and differentiability and a couple of like high order derivatives. Anyways, if you liked the video, please like, comment, and subscribe. Also, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated, and feel free to join my Discord. And yeah, I will see you guys in another video.